What if the solution to cleaning up space was not about capturing debris at all, but about repurposing it? Earlier this year, researchers published a remarkable proof of concept in Advanced Manufacturing, part of the Nature family of journals. They demonstrated that orbital-grade aluminium debris could be recycled through additive friction stir deposition into high-quality feedstock suitable for printing new parts. In plain terms, the derelict satellites that currently pose such a hazard in orbit might one day become the raw material for their replacements, fabricated directly in space. This work is not an isolated curiosity. Several other papers published in 2025 across journals such as Acta Astronautica and the Journal of Manufacturing and Materials Processing are pointing towards the same conclusion. In-space manufacturing, underpinned by additive technologies, could become central to a sustainable future beyond Earth. Earth's orbit has become a junkyard. Today, space agencies track over 36,000 large pieces of debris, each more than 10 centimeters across. Add to that millions of smaller fragments moving at nearly 28,000 kilometers per hour, and you begin to see the scale of the problem. At those velocities, even a paint chip can puncture a spacecraft. The real fear is something known as the Kessler Syndrome, a runaway cascade in which one collision generates fragments, which then cause more collisions, until low Earth orbit becomes unusable. The consequences would be severe. Much of modern life, from weather forecasting and navigation to communications and financial transactions, depends on orbital infrastructure. Attempts to address the problem range from tracking systems to capture devices such as nets and harpoons. Yet, as Abdul Hamid and colleagues concluded in their 2025 review in Acta Astronautica, the growth of debris is outstripping these measures. Their assessment suggested that if we are to sustain space activity, a more radical solution is required, which brings us to the idea of treating orbital junk not as waste, but as a resource. This is where additive manufacturing enters the conversation. The research offered tangible evidence that recycled aluminium alloys, similar to those used in satellites today, can be refined through additive friction stir deposition. The process not only reduces porosity, but improves microstructure, producing a material that is, in some respects, superior to the original. Meanwhile, the European Space Agency's Clean Space Initiative has been investigating how to deal with more complex debris streams, including alloys with coatings and composites. Their work focuses on ways of consolidating these heterogeneous materials into usable inputs for orbital printers. From a systems perspective, Jose and colleagues writing in the Journal of Manufacturing and Materials Processing argued that in-space manufacturing offers not only a way of reducing waste, but also a strategy for minimizing launch mass and enabling on-demand repairs. They framed it as a sustainability lever in its own right, a means of lowering costs while enhancing mission resilience. The attraction is obvious. Every kilogram of material that does not need to be launched from Earth represents a saving of tens of thousands of pounds. Every component that can be fabricated in orbit reduces dependence on fragile terrestrial supply chains. So how might this vision unfold in practice? Imagine a derelict satellite being intercepted by a purpose-built service craft. Robotic arms secure it, stabilize its motion, and prepare it for dismantling. Panels and structures are cut down, then processed into rods, powders or wire, depending on the needs of the downstream additive process. From there, the material enters a printer housed within a shielded orbital chamber. Layer by layer, new components are built up. Gupta and colleagues in their 2025 review for Acta Astronautica suggested that the most practical early products would be CubeSat frames and other relatively simple structures. They also pointed to brackets, shielding panels, and antenna elements as realistic near-term applications. What begins modestly with small satellites and replacement parts could evolve towards entire modular systems manufactured from what once was waste. And the benefits extend beyond cost. Fabrication on demand means less risk of mission failure and a meaningful step towards a circular economy in space. Looking further ahead, the implications are profound. One can imagine a circular orbital economy in which factories continually recycle debris into fresh structures, trusses, solar arrays, or even entire satellite buses. This is the vision Abdul Hamid's team described, factories in orbit producing what missions require without recourse to Earth. Push the thought experiment further and you arrive at Mars. Crews landing with printers rather than cargo holds full of spares, fabricating what they need from recycled metals or local regolith. Lunar bases constructed from native resources, supported by additive technologies that remove the dependence on costly supply chains stretching back to Earth. Yet, challenges remain. José's review was careful to note that material variability, printer reliability, and orbital energy requirements are far from solved. Gupta emphasized the regulatory uncertainties. Under existing treaties, debris technically remains the property of the nation that launched it. So who exactly has the right to harvest it? And beyond law, there is the ethical question. When does a defunct satellite stop being property and start being common resource? The engineering hurdles are matched by these governance dilemmas. But the trajectory is unmistakable. Additive manufacturing is moving to the center of any credible plan for sustainable, long-duration spaceflight, which brings us back to the present moment. For decades, orbital debris has been seen as a threat, a hazard to the continuation of space exploration. The research of 2025 suggests something more optimistic, that debris can be reframed as feedstock, the raw material for a new phase of human activity beyond Earth. Baker's experiments demonstrate feasibility in the laboratory. José's systems analysis shows how it fits into broader mission planning. Abdul Hamid has outlined the technologies required for orbital factories, while Gupta's review ties the whole narrative to the wider theme of sustainability. Taken together, these studies indicate a shift. What sounded speculative a decade ago is now being tested, reviewed, and seriously debated. The idea of printing satellites from debris is no longer a flight of fancy. It is becoming a research field in its own right. So the next time you look up at the night sky, remember this. The clutter circling our planet today could very well become the scaffolding of tomorrow's space economy. It is not merely about cleaning up orbit, it's about building a future where humanity lives and works in space without leaving behind a destructive legacy. If you've enjoyed this episode and want to hear more explorations of how additive manufacturing is reshaping our world, and as we've seen today, even our future in space, do make sure you subscribe. Subscribing means you won't miss the next conversation. And if you found today's topic thought-provoking, please consider leaving a review or sharing the episode with a colleague. It really does help us bring more voices and ideas into the discussion. Until next time, thank you for listening, and keep looking forward to the future we're building layer by layer.